So we want to induce characters from H to G, and for that we need a formula to induce the characters. So this is the formula which is most useful for computations. So purpose of this lecture is to actually prove this formula. Here the CG stands for the centralizer. This C stands for centralizer. So let us start by giving some introduction and then going through the proof. So let this G represent the conjugate elements conjugate to G in the group G. So now you go to a smaller group, because we are working with H as a subgroup of G. You go to a smaller group, you take the intersection. So this is called restriction to H. So things which are conjugate here may no longer be conjugate here. So this we have seen in S5 and A5. Things which were conjugate in S5 may no longer be conjugate in A5. So might not be conjugate. So they might not have the same conjugacy class. However, we can still split this as a union of conjugacy classes, since anything which is conjugate in H will automatically be conjugate in G. Obviously G is bigger, so whatever is conjugate in G may not be conjugate in H, but what is conjugate in H will be conjugate in G. So they are also conjugate in G. So what we need to do is we need to split this into conjugacy classes so that we can sum up over it. So obviously we have just seen in the previous lecture, the game is all about conjugacy classes. So we have no option but to split this as conjugacy classes. So you express this as a union here, where xi are the representatives of the H conjugacy class. So you can, and this is a disjoint union. So you want it to be a union so that you can sum up over it. So you're given such a statement like this, and let G be an element of group, this psi be a character of H. If M is 0, then the induced, so this M, if this M is 0, then obviously induced character has to be 0. Otherwise you have this formula. So let us start with this M is 0. If M is 0, then all the elements X in G, so X inverse Gx is in H, is just the null set. This is 0. Nothing much, because if you're putting M as 0, then there is no xi here in which you can split your conjugacy classes. You do not have conjugacy classes here, so you just have to put 0, nothing else. There are no conjugacy classes for M is 0, so this set has to be empty, and therefore this is 0. So the first part is clear. So by definition, because if this math ring, this thing is 0 and you're summing over this has to be 0 by its definition, which we have just given in the previous lecture. So now focus on M greater than 0, and you express this as a disjoint union so that you can sum over it. So you have this disjoint union where you define each xi like this. All the elements in the group, so that X inverse Gx is in H, because you have to still keep this, but now you're summing up over conjugacy classes. So it's conjugate to H in H to xi. So what we will use is that if X belongs to xi, then X inverse G of X, this lies in H and is conjugate, so should be H inverse xi H. So if this portion, so if X lies in xi, it should look like this. So this is what we are going to repeatedly use for xi. So this is what we mean. So now the disjoint union helps us summing. So this is our formula for induced. Obviously here we said that every element is 0, so you sum up over 0, you get 0. So now you're saying M is greater than 0. So X is in G, so obviously we were saying that we want a disjoint union like this. So you're using a disjoint union. And then you can, instead of this math ring here, you just go to psi here. So that is the entire purpose of constructing this xi, is that you just work with something concrete, this psi here. So that is it. And now you start summing it. So X is X in xi, so this X inverse G of X, these are all conjugate classes, they are all conjugate to xi. So this is a class function, so it's going to be the same over xi, because all these elements are conjugate in H to xi. So it becomes this psi of xi, and this becomes obviously now you're summing it over xi, so for every xi you get this size of the set, psi of xi. So till this point it is clear, just because of a construction of this disjoint classes. and we know it's a class function. So nothing much has been done. So now we need to prove this equal to this. So to prove this, we have to show that this portion is equal to size of these centralizer classes, this over this. So once you prove, instead of this here, you write this, then you just get this formula, because this doesn't have any I in it, so it will jump out like this. So it'll be done if we show this. So we have to show this. So what we are going to show later on is this is a double coset. So later we will show that xi, this disjoint union, is just this centralizer G, GIH, a double coset. So we'll show this later. Assuming this is true, let us prove that this holds. If we assume this is true. So before we do this, let us recall what a double coset is. So we have to show this, and we have to assume this is true, and this we are going to show later. So we assume this is true, and we will show this later. So double coset. So let G be a group, H and K be subgroups. So H acts on G by left multiplication, K acts on G by right multiplication. So for each x in G, HK double coset is of this form, and the size is given by this formula. So we are going to copy this exact thingy here. So that is it. So obviously you can interchange x and x inverse, doesn't really matter. So we are going to copy this here. Size of this group is this, so you H and K. So here you can say this is H and this is K, and then you're using this formula right here. Just interchanging x and x inverse, that doesn't really matter. So right here. So now you notice that this CG is a centralizer, as we have been talking. Both of them are centralizers. This and this is also a centralizer. So since this is a centralizer, you can take this G inverse inside. It's going to commute. You take this inside, and this is precisely what is xi. So we will also talk about this later on. We are actually going to choose this GI so that we get this xi. So this is also to show later. So if this is xi, now you replace this with xi here. Now H intersection the CG xi will just give you the centralizer in H, because you see intersecting a centralizer. So this is what you get, and so this is pretty much it. So now take this on this side, xi over H gives you this, and that is what we wanted to show. Now we are left with showing this and this. So let us prove this, and then we will prove and during the course we will also show this. So we want to prove this equality. So first we are going to show that this holds, so this is a subgroup of this. Then we will show this xi is a subgroup of this, and then that's how the equality will follow. So this is what we want to show. You fix an I and choose some GI such that this holds. So that is exactly what we wanted to show here. So this is what we wanted to show here, right here. This just comes by choice. It is possible because xi is after all just conjugacy classes. So you can put something like this. Now C lies in the centralizer and H lies in H. So you form something like this. You open it up. Now the C and G will commute because again C is in centralizer. So you pull C here. You have pulled C here. So these two will cancel. Now you have this thing here. Precisely this. So you're putting in xi here. So what we have shown, we have started from here, and this is equal to this. So this is precisely of this form. So notice that when we began the lectures, we said partition into disjoint functions xi, and we said if x belongs to xi, this thing should hold. Now instead of, so this is exactly this, and here instead of x you have CGIH, and we are saying x is in xi, then this holds. So instead of x now you have this, so that means that CGIH is now in xi, just from this important statement. So at the start of this lecture or on the previous slide we talked about the importance of this. So this belongs in xi, so there you have the first inclusion. This belongs to this. So now we have to go in the reverse direction. We'll start with x and xi and show this x lies within this. So that will, you'll have the reverse inclusion, and that should give you the equality. So x is in xi, h is in h. Again copy this definition up here because that's what it means to x in xi. You copy this here. So instead of xi, you put this thing, equality, right here. So now you have this equality. Now you transfer x inverse to this side, so that will become x here. You transfer this here, it becomes x inverse here. That is precisely what we are writing here. So thus this, so this, now you have, and here you're putting x inverse here, so this you have here. So see, now these elements are in centralizer because they are fixing kind of G. So now this is in centralizer. So if this is in centralizer, then obviously x would belong to CG, this G. You're transferring these two on this side. First transfer D, G, then transfer H. So x belongs to this. And that's what we wanted to show. X belongs to xi means x belongs to this. So we have shown the reverse inclusion, and therefore you have the equality. So that is the end of the story.